Happy Fest Day, Joe. I took you at your word. You don't want to call it your birthday. I've done a lot of these things in the past, more than probably any human being on Earth. And I keep promising every single time, that's the last one. I'm getting too old. You always risk, the border between being a hero and being an old fool is a very narrow one. So I would like to stop this before, but nevertheless, Joe is too important to me to not do this. Joe, as you all know, is a great physicist. And like all great physicists, he has his blind spot. Newton couldn't understand wave theory of light. Einstein had trouble with quantum mechanics. Steve Weinberg has terrible problems with two-component spinners. David Gross does not, never mind that. With Joe, it's positive and negative numbers. Once, it was 2002, I think, we wrote a paper. I was trying to explain to Joe the problem, and Joe wasn't getting it. He simply couldn't get the point that I was trying to make. We tried and tried and tried. I don't remember where it was. Was it here? It was at Caltech. Good. It was at Caltech. What was the occasion? It was somebody's birthday or something? I don't remember. And I kept explaining and explaining, and Joe didn't get it, and he didn't get it, and he didn't get it. And finally, Eddie Farhi's sister was sitting across. Now, Eddie Farhi's sister knows nothing whatever about physics. I think she, at one time, was a math teacher. She was also famous for having dated Schwitz, if you're not Jewish and don't speak Yiddish, literally, he was a wrestler. Oh, he was a professional wrestler. And Schwitz, I can't say it. It means fountain of sweat. Anyway, she was sitting opposite from us. She leaned over and she said to Joe, I think he's trying to tell you that the sum of two positive numbers is positive. And all of a sudden, Joe had an epiphany. And within 2 minutes, he had solved the whole problem. But he needed that hint. No, I looked today. I tried to find the acknowledgement, and I couldn't find it. Okay, good. But this did happen, and it happened exactly the way I said. So I went back, and I tried to see if this was a problem that Joe has had for many years, and I discovered it goes back to his childhood. I managed to extract out of the internet a photograph of him from the 3rd grade, and as I understand it, this was a 3rd grade remedial arithmetic when he was called to the blackboard to explain a homework problem. And I want to point one thing out to you. I want to point out the equal sign there. There's not an arrow. Are you getting better at it, Joe? Okay. So let's get down to physics. What's that?
Your mic is too close here.
Oh, am I?
Your words is missed.
Oh, that's terrible. And my beard is in the way. Old fool, I told you. It was a sharp line. Okay, is it better? Yeah, I'm not going to repeat the jokes. Okay. Okay, let's get to physics. My favorite episodes in physics, the ones that I sort of admire most, are the ones which are initiated by the confrontation with conflicts of principle. Conflicts of principle, two things, both of which have to be true and both of which can't be true together. I think you all know lots of them. The speed of light and Einstein, Boltzmann and his furious battle with the second law of thermodynamics. And when these things come along, real progress happens. Real ideas emerge. Those ideas are often revolutionary, and they tend to change entirely the way we think about physics. We're very lucky when they come along. It means we can make progress, and we don't have to wait for our experimental friends to stop sitting on their asses and doing nothing. We are fortunate in having such a paradox now. The paradox is, of course, the AMPS paradox. Mary, Marolf, Polchinski, and Sully. I always have trouble remembering what AMPS stands for. But it's a real paradox. It's a hard paradox. And my guess is it's going to exist in the history books of physics. It's a permanent contribution to physics. But I also think that the reason that it's so important is not because there are firewalls, but because there aren't firewalls. In extracting ourselves from this very, very strange and interesting puzzle, we're going to have to create new ideas. We have basically found that everything we were thinking about black holes was too easy, too simplistic, and that the problems are much, much harder and much deeper. It's going to require brand new ideas, some of which I think are out there, some of which are beginning to be out there. And what I'm going to talk about is two ideas that I think are going to play a role in the final story. Both of them I've been involved in. One with Juan, one pretty much by myself. Oh no, one with Steve Schenker and Douglas Stanford. And I'm going to talk about them. One of them is, I would call, if I were to give it a name, Juan called it ER equals EPR. You know what that means, or if you don't know what it means, I'll tell you right now. It means that entanglement builds bridges, Einstein-Rosen bridges. That's one idea that I think is going to play an important role, and the other has to do with computational complexity, a subject which physicists don't tend to know much about, except unless their name is John Preskill, and which comes largely from computer science, and I'm going to tell you why I think it's important, unless David shuts me up before I get there, but that's okay. All right, imagine two black holes are created. Let's just suppose they're created at some, David, do you have a? Oh. No, not you. Not you. We know that you can't shut me up, come on. We have a long history of trying to shut each other up. Let me get my stick, just in case David attacks me. This belongs to Rob, of course. So let's assume a black hole is more or less created at time t equals 0. Two black holes. Two black holes are created, and they happen to be created in a particular funny kind of state, which is a state which is maximally entangled. Right? There they are. Bob is going to jump into one black hole. Alice is standing at the other black hole, and she's going to do various manipulations on it. She has a very powerful quantum computer. She can even stick the whole black hole into the quantum computer and let it do things to the black hole, the sorts of things that quantum computers do. And we're going to assume that Alice can basically do any quantum process on her black hole that's consistent with quantum mechanics. And Bob, well, he's not so good at all this. He's just going to jump into the black hole and see what he sees. Okay? These black holes are highly entangled, maximally entangled, or almost maximally entangled. And that means, now what I'm doing now is, roughly speaking, stating the AMPS paradox. The AMPS paradox begins by saying, consider a mode of the radiation field right outside the horizon. Just outside the horizon over here. By assumption, that mode is entangled with a degree of freedom on Alice's black hole. It might be right over here, and we could call it B prime, or whatever we want to call it. And these two are entangled. Okay, the way I'm going to state the AMPS paradox is a little bit different than the way they stated it. And I'm not going to prove anything. I'm just going to tell you what would be true. If B, well, all right, let me state it the way they stated it. If B is entangled with something over here, it can't also be entangled with something just on the interior of this black hole. And if it's not entangled with the interior of this black hole, it must mean that there's a particle, the vacuum is somehow screwed up, and there's a particle coming out of here. Another way, and if it's true for one mode, it's true for all modes, and therefore there's a firewall over here. That's the argument, very simple. I want to state it a slightly different way. If B is maximally entangled with something over here, it must mean that the degree of freedom just behind the horizon, which is supposed to be maximally entangled with B over here, must in part be made up out of degrees of freedom over here. If B is entangled with what's supposed to be over here, and what's supposed to be over here, and B is also entangled with Alice's end over here, then it must be that what's over here is in part anyway composed of Alice's degrees of freedom. Now that sounds crazy. It sounds crazy because Alice can then do an experiment which measures something which is entangled, or at least partly entangled, with B over here, and in the process create a particle just behind the horizon here, moving toward the singularity. And if that's the case, we have a very peculiar puzzle. These two black holes are very far from each other. Bob is going to jump in. He's going to experience a particle that was caused by Alice doing something on this black hole over here. That's peculiar, because if these two black holes are sufficiently far apart, you'd expect that there's no way that Alice can affect what happens right behind Bob's horizon, okay, if they're far enough away. Okay, so what does AMPS conclude? AMPS concludes that this particle, which I didn't draw, this particle must have been there independently of whether Alice actually did what she said she did. The particle must have been there because there was no way that Alice could have created it, and therefore there must be a firewall coming out, or not coming out of this black hole, but just on the interior of the horizon. That's the basic AMPS argument. And the basic counter proposal is, no? The basic counter proposal is the idea that entanglement creates bridges. Einstein-Rosen bridges. I'm not going to explore. Juan talked about it. I'm going to assume you followed his lecture. That a wormhole is there as a consequence of the entanglement. If that wormhole is a short wormhole, and wormholes can be quite short, these two black holes could be as far apart as you like, and the wormhole can be short, then what Alice did over here has the potential of creating a particle behind Bob's horizon here just by sending it through the wormhole. That's the basic counter proposal. And once you say that, there's no more need for a firewall. Yes, Alice created a particle by doing something over here that went through the wormhole, and Bob hit it when he fell in. Nothing, no big deal. I think that's the right response to the AMPS paradox, but it requires a totally new idea. The totally new idea is that entanglement builds bridges. Okay? ER equals EPR. Okay, now, this raises, all right, here's a picture of it. I'm going to, excuse me. You've all seen squares. Oh, incidentally, Steve, I think we should make it a requirement for people in our theory group that they can draw good squares, because this seems to be the basic mathematical tool of our trade at the moment. This is the Penrose diagram. It's a Penrose diagram not of two black holes in empty space, but two black holes in ADS. The right-hand side is a black hole. The left-hand side is a black hole. The fact that they're touching in the middle here is an indication that they're highly entangled. I won't try to explain this. Juan explained it. And I'm going to assume one more thing. I'm going to assume that these two black holes were actually created at time equals 0, that the past is a fiction. It's roughly speaking like thinking about cosmology. We have an expanding cosmology in the future. The past, contracting cosmology, let's take to be a fiction, a useful fiction, but let's imagine that this black hole was created at time t equals 0. Alice wants to send a signal to Bob. She's going to send a signal through the wormhole. This is through the wormhole. It's going to hit Bob. Bob may collect it. This is what wormholes do. But it creates a new opportunity for firewalls. The new opportunity for firewalls is if Alice is really unpleasant. She can put a bomb over here and send it through. and perhaps she can kill Bob. But from this diagram, it doesn't look like she can kill Bob. It looks like the best she can do is send her bomb up to the singularity with Bob hitting it, Bob not hitting it before he gets to the singularity. Well, on the other hand, if Alice has this magical wand, this quantum computer that can do anything on the left-hand side, she can do something that's called activate a precursor. A precursor is an operator. This W here means a perturbation that would send a signal to Bob. Send it from the past. But there is no past. But what Alice can do is simulate an operator from the past by a simple mathematical trick. She can apply not the W at this time, but the conjugation of W by the time development operator between here and here. The result of applying this operator is exactly the same as having applied the operator W down below. And what's really going on is Alice is applying an operator not on the boundary of ADS, but a non-local operator on ADS. If this is a local operator and you run it in time, what you find is a highly non-local operator over here. If Alice's magic wand can activate non-local operators of arbitrary complexity, she can act over here with the effect of creating a signal in the bulk over here that's exactly the same signal that would have come from here. So, in principle, if she has this magic wand here, she can send a signal and hit Bob. That's a new opportunity to create firewalls. All right? Now, it doesn't happen unless Alice decides to make it happen. But wait, how do we know that? How do we know that the environment surrounding the left-hand black hole, by that I mean a bunch of particles which might interact with the boundary, bounce off it, an environment that really would constitute the rest of space-time beyond the two black holes, how do we know that these particles can't activate exactly the same kind of operation that could also send a bad signal to Bob? What's the principle which would tell us that Alice can activate a very complex operator, but that a whole bunch of environment, a large amount of environment, interaction of the radiation with large numbers of particles, can't do the same thing? After all, there's a lot of dust out there. The Hawking radiation, or a lot of dust, in this case of two black holes, a lot of dust could have the possibility of activating something which sends a signal to Bob. That is the new firewall argument, or one new firewall argument. Okay, so that seems to be a replica of the same. Yeah.
In that setup, are you assuming that the dust has turned to pure state and is leaking into another pure state, or the more realistic setting where it is?
Measure. I don't think it matters. But let's take the simple case where it just acts on it and acts on it as it leaves it in a pure state. But we can discuss the other case too. It leaves it in the pure state of the left side black hole. Wait a minute. The left side black hole is not in a pure state to begin with. Yeah, operating with. But you can take it to be unitary operated. It also acts on the dust. The dust could be thought of as part of the system. Okay, so now what I'll tell you is.
After the dust acts, are the two CFDs together still in pure state?
No, they could be in a pure state together with the dust.
Oh, so they could be in a mixed state.
They could be in a mixed state. They could be in a mixed state. Yeah. But I'll think about the case where Alice just acts with a unitary, leaving it in a pure state, and then we can discuss whether it also applies to measurements. I don't think there's any real difference. Okay. So the question then comes up. The natural question that comes up is just how hard is it? How difficult, how complex an operation is it to send this signal? Alice has to work very hard to create this precursor. It's called a precursor, the operator acting over here, which simulates the operator over here, and which creates a signal over here. Can dust do it? Well, that's a question of just how complicated a process it is. If it's sufficiently complicated, probably dust can't do it. If all it takes is the interaction with, let's say, S being the entropy of the black hole. If all it takes is an interaction of every Hawking photon with some dust cloud, then it'll happen every time. So the question is, how hard is it? And this is a question, I believe, of computational complexity. The same kind of computational complexity that computer science scientists think about. So let me begin to analyze it. I don't know if I'll get to the end. It doesn't matter. At this point, I've told you really what I have to say. That it's a question of computational complexity. Yes, David? Yes. Yes. No, good. The question is not whether Alice can send a firewall. I believe she can. I believe she can. If she can't, then the hell with her. Then it's even better. Then we don't have to worry about it. I believe she can. I think Juan, also would probably agree with me that she can. The question is whether it's something. How likely is it to happen in nature? There are things which are so incredibly hard that they're very unlikely to happen in nature. No, it's not a paradox. Alice can do this operation. Now we want to know, Bob is going to jump into the black hole. How much of a risk am I taking? Okay, that's the kind of question. So very odd things can happen in this room. I mean, the air can suddenly freeze or God knows what. You would say that's very unlikely, so we shouldn't worry about it. That's what I'm asking, whether this is something that's likely to happen in nature or so incredibly unlikely that it takes something as complicated as making all the air whoosh into the corner of the room to happen. I think this whole question is very closely related to Boltzmann's problems with the second law, but let's talk about it. Okay, so there's a model of black hole evolution which I will use. It's not essential, I don't think, but the model is the Hayden-Preskill model of black hole evolution, and it's simply a quantum circuit. So what does a quantum circuit mean? It means a collection of qubits, and the qubits interact in pairs, and in between every time step, half the qubits pair up with the other half of the qubits in some random way and interact through gates. A gate is simply a two-body, two-qubit unitary operator. And then in the next time evolution step, they rearrange. It's easier to draw the green boxes all in a row like this and rearrange the qubits than to try to draw the qubits jumping over blue lines. So they rearrange in a random way, and then again, and then again, and then again and again. And this is the evolution of a black hole. I'm not going to try to defend it. I'm just going to tell you it looks like a useful picture of how a black hole evolves. Okay, I'm going to define for you now what computational complexity means. To go from here to here, there's some unitary operator. Supposing I give you a unitary operator, and I ask you to simulate it or to implement it on this quantum circuit. In other words, I ask you for a system of gates which will take you from here to here with some number of steps in some amount of time and give you out the output, the unitary operator. The minimum number of gates that it would take in any circuit whatever is called the complexity. It's a generalization of the idea that the complexity of a problem in classical computer science is how many steps it would take a Turing machine to implement to solve the thing, or to do what you want it to do. That's the idea of computational complexity. Can we run the clock backward? No. Okay. So let me give you some examples of landmarks in the time evolution of a circuit. The first interesting landmark is the scrambling time. The scrambling time is the time that it takes every qubit to interact either directly or indirectly with every other qubit. Okay? That's easy to figure out. In the first step, every qubit interacts with itself and one other, 2 qubits. The second time step, it's interacted with 4 qubits, 8, and so forth, 2 to the number of steps. Now, when 2 to the number of steps is equal to the total number of qubits, and I'll take the total number of qubits to be the entropy, right, then that's log k. Number of steps is log k. And there are k gates, or k over 2 gates in each step. So the total number of gates that it takes to scramble is k log k, or s log s, where s is the entropy of the state at any given time. That's called scrambling. That's the scrambling time. And basically, it's the time after which you couldn't tell by looking at small number of qubits that it isn't completely equilibrated, that it has not gone forever. Is that the maximum complexity? Now, I think some fundamental mistakes were made in this business by thinking that scrambling is the same as maximal complexity. My own guess is that at the final end of the circuit, when it's run for as long as it can run and not just iterate the same stuff over and over again, probably there are firewalls, I think. But how long does it take until you reach maximal complexity? All right, now there's a theorem. Any unitary can be constructed by an exponential number of gates. More than that, almost all unitaries take an exponential number of gates. In other words, starting with some simple state, if you want to get to a generic state, it takes an exponential number of gates, an exponential amount of time. So if you were to plot the complexity as a function of time, it linearly increases for a while, but then by the time it's exponential, there are no new states to access. And it simply tops out at a complexity which is exponential in the entropy. Yeah. Exponential in the entropy is the maximum amount of complexity you can have. And scrambled complexity is just S log S, a tiny, tiny amount. So whatever scrambled is, it's very, very, very far from what a generic state is. Of course, a generic state is scrambled, but a scrambled state is very, very far from a generic state, extremely so. On the other hand, what goes on up here is kind of quite mysterious, especially along here. It's not entirely intuitively obvious what is contributing this complexity, but it is true. Okay, let's come back to these precursors. Alice's precursor wand, if W, which W was the operator that she had to activate to send the signal in, let's suppose that's unitary. And just stop, you know, when I'm finished, just tell me and I'll stop. But I'll keep going as if I was going on forever, or at least an exponential amount of time until you stop me. Okay, I'm already scrambled, so. Okay, remember what we have to do. We have to take W and conjugate it from the left with U and conjugate it from the right with U dagger, where U was the time development between the time Alice actually did her operation and the time that she was trying to mimic when the operation happened. All right, now it is true. So what does that mean? That means you run your circuit, you hit it with W, and you run your circuit back. You can estimate the complexity of the operator, of the conjugated U dagger. It's also a unitary operator. You can ask how many gates does it take to make it. And the answer is about twice the number of gates that it takes to make U. So again, the complexity of a precursor increases linearly, and they get very complex. I'm not going to get through this, so I'm actually willing to stop right here if you want, and more can come up in the questions if we like. Okay, there's more. Obviously, there's more, but you know, I'm not going to try to rush through more than. If things come up in the questions, I'll just keep going. If things answer the questions, so let's. Well, what I should say, excuse me, wait. I have half a minute. Let me just say what the bottom line is. Let me just say what the bottom line should be clear. Two things should be clear. First of all, the idea that a black hole has, that a generic state of a black hole has a firewall is quite possible, but the time that it would take to get to the generic state is exponential. By that time, real black holes have long evaporated. And The second statement is if Alice wants to do this by precursor, it's an incredibly complicated thing that's about as complicated as reversing the second law in this room and creating some anti-diffused fluctuation which goes into the corner of the room. Okay, now I am finished.
Questions?
Lenny, I'm here.
I hear Raphael's voice, but I can't see. Okay, good.
Right there. So the air molecules that freeze in the room, there are many such states,
Right.
and I can take linear superpositions of them, and I'll always get frozen air. I'll never get, by linear superposition of frozen air, normal air. I don't think the same is true for complex versus simple states. I think I can take linear superpositions of one kind and get the other. And so it seems to me that the significance of whether they're firewalls or not
That's true after the recurrence time. I think up to the recurrence time, there really is a Hermitian. Complexity is a kind of clock. That's the way I've learned to think about it, and I learned to think about it that way from Scott Aronson, that the onset of complexity is a clock. And in fact, there is a Hermitian operator which can measure the complexity. Up to the scrambling, not the scrambling time, up to the recurrence time, when you start recycling states, and then states after the recurrence time become linear superpositions of the earlier ones. And I think that's correct.
Well, I think you're picking out a time when the black hole was simple.
Yes,
And-
you
and
start with
using that as a-
we start
yeah.
with a time that the black hole is
But you also gave yourself the freedom to have a very powerful wand or quantum computer. So I could simply prepare a list of states that span the Hilbert space, and
Yep.
and they would look like they have firewalls in one basis, but not in the other.
Well, I would say that most states have firewalls. You're asking about this linearity question, aren't you?
Right.
Oh. You know, I don't fully understand the answer to that. I understand what the question is. I think maybe there is an element of nonlinearity that goes with these ideas of entanglement. So I understand what you're asking. I don't have a simple answer to it. It confuses me. What I would like to know is there an operational experiment that somebody falling into a black hole can do that would discover that the laws of quantum mechanics are not right, and I don't see one.
Don?
Okay, so my question was along the same lines, but you say you're not sure whether there's a Hermitian operator or not.
Well, I know that there's a Hermitian operator, which is a kind of clock operator, that will keep track of things up until the recurrence time.
Well, let me make the following comments. If you define your notion of complexity as a linear Hermitian operator,
Up to the recurrence time. Yeah, I think I can even write it
and
down for you.
if most states are maximally complex, then if you happen to have dust that interacts in such a way to give you a maximally mixed state for the black hole, then the black hole with high probability has a firewall, according to what you said.
Sorry? If you wait for a time longer than the recurrence time, I suspect there will be a firewall.
My comment is that if you have a black hole which is maximally mixed, okay,
Maximally mixed with what?
anything, does it matter?
Okay, yeah.
Okay.
No, that's wrong. That's just wrong. You have to include the dust. The dust is part of the thing that connects to the wormhole. It's simply part of... If you can't send a signal to Bob by activating and multiplying by these operators, I believe you can't send a signal by measuring them either. Because measurement is just a... yeah. So I don't think that's right.
Aaron?
So Lenny, you had a picture where these two black holes were
I can't
created.
see you. Was that Aaron Wall?
Yes.
Yeah, okay.
So you had this picture on the slide where the two black holes were created at time t equals 0,
Right.
and you said Alice and Bob can't hit each other. She can't send in a signal that will hit Bob.
Which one? This one?
That one, without creating the precursor. She can't just send it in causal.
Say it again.
I'm just summarizing right now what the slide says. That, she can't just causally send in a signal from the boundary that hits Bob because she's stuck at t equals 0.
Yeah.
But that seemed rather artificial to me because if you didn't start at t equals 0, you could just take an Alice that was earlier in time, and she could just send the signal in directly without the precursor. So I'm confused. What is the physical significance of this idea that you're starting at t equals 0?
Okay, I think the physical significance is very similar to in cosmology. When you say a contracting cosmology is unstable, I think this is unstable here. I think if you do start in the past, you have a very high probability of just any little fluctuation making something bad. But for the same reason that you would say we shouldn't start in the remote past in cosmology with an unstable situation, we should imagine the universe was created reasonably smooth, and we should evolve it from there. I think the same thing is true of black holes. Now, keep in mind that a real black hole, when it is created, has a smooth horizon. At creation, it has two things. The first thing is that it has a smooth horizon, and the other thing is that the Einstein-Rosen bridge, well, if it's only a single black hole, it doesn't really have a bridge, but it has something very similar to a bridge. Let's see if we can find it. All right, here's Juan's picture from yesterday of the Einstein-Rosen bridge expanding, stretching out. I think the important point about this stretching out is that it tends to redshift signals along here and dilute them and make them less potent than they would have been had the stretching not been taking place. If the opposite of stretching were taking place, contraction, things would be unstable. They would be unstable for the same reason that they're unstable in cosmology. In a contracting phase of de Sitter space, you can easily, ruin the de Sitter space. This expansion that's taking place, I think, is important to the stability of the black hole. And for the same reason, you shouldn't start a cosmology. But the main point is that real black holes start with two features. The first thing is the starting point of the black hole is smooth. The second thing is that it's stretching, not anti-stretching. So, for example, here's a black hole that was created, let's say, by an infalling shock. An infalling shock creates the black hole. At first, the horizon is clearly smooth because it's just good old flat space. And with time, the Einstein-Rosen bridge in here stretches. So it starts with two features, smooth and stretching. I believe that's something that you should maintain in your model of black holes in the anti-de Sitter space, that it's stretching and that it's smooth. So that's something I would insist on. You cannot insist on it, and then you'll get then you'll get firewalls. That's true.
More questions? So in the original S paradox, there was one black hole that was evaporating, and to get to your picture, you've got to collect all the radiation and turn it into a second black hole in the thermal field state, which is a computationally very complex process. So in some sense, the original AMP situation is computationally complex. So why doesn't it give you what you think is the typical situation?
Which is the original situation?
The evaporating black hole.
No, I don't think so. If you think of it as a two-sided system, you must always think of the evaporation as the other side of the black hole.
Right. But it's computationally complex compared to the thermal field two-side, because
it's computationally complex. But how computationally complex? Power law. Polynomially complex.
You think you can turn Hawking radiation into thermal field state in polynomial steps rather than?
No, you can start with the initial smooth state and turn it into the combined two-sided system in a polynomial time. And it's the two-sided system that I think you have to follow. You can't analyze the interior of the black hole in a pure one-sided situation. You've got to be, after the page time, you'll have to be thinking of it as a two-sided system, assuming that this idea of entanglement creates bridges.
But very far from the thermal field state.
Very far from the thermal field state, but very far from the generic state. It takes a time of order e to the s to create the generic state.
Do you believe that?
More questions? Well, if not, do you want the last 2 minutes, or?
Let's see. What's the most important thing that's interesting? Okay. All right, there's a very important set of facts. There's a black hole. There's a sense in which I think the black hole is an onion, a layered structure. Look at it. And this could be a one-sided or two-sided black hole. Look at it here. And I think the different layers have different levels of complexity in the following sense. Consider an operator over here, a unitary operator in the bulk. How complex is it when it's written in terms of operators on the boundary? The boundary operators will also be unitary, and we can ask how complex are they in the boundary field theory. So one way to calculate it is to say, let's go to the edge of the onion over here. We use the Hamilton-Cabot-Low-Lifshitz construction to say that the operator over here can be rewritten in terms of operators in this triangle here. The time span of this triangle here determines the complexity of the operator here. We have to take all of this stuff here and pull it back to t equals 0 in order to give an operator in the Schrodinger picture. And the complexity that we generate from that will be dependent on this time here. So it's quite clear that the deeper into the black hole that you go, the more complexity you will generate for the expression for an operator in terms of the boundary field theory. There are some landmarks. There are some landmarks. I'll tell you what the landmarks are in a picture. There is a landmark of complexity, which is just complexity 1. In other words, just a very simple operation, that corresponds to a signal being sent from about the ADS radius from the horizon. In other words, from far macroscopically out. There's a complexity associated with S, a complexity of S. Now, a complexity of S is what you would expect for an operation which hits every photon, but which hits every photon in a simple way, just a product operator which hits every photon mode. That would be expected to have a complexity of order S. Why? Because the number of gates that it would take to make an operator which was just a product of a whole bunch of modes is just of order S. And it turns out that that corresponds to a layer of the onion which is only a little bit in from the absolute minimum complexity and cannot send a signal that would be very destructive to Bob. The real destructive signals happen at complexity S log S. That's the scrambling complexity. Okay, that's the scrambling complexity, and that sends a signal from a distance which is L Planck, the Planck distance, and that signal will be felt by Bob as a Planckian collision. And then you can keep going. You can make more and more complexity. Whether it makes any sense at all to think of distances smaller than the Planck distance, I rather doubt, but you can definitely think of complexities beyond the scrambling complexity. If you define with an appropriate definition, I like the phrase that sub-Planckian distances really mean trans-scrambling complexity. But we don't know very much about that. So this S log S complexity is a great deal more than just S. This is the dust cloud. This is the dust cloud hitting the radiation. This is reaching in way deep into the black hole and sending a signal from a Planck distance. So anyway, my point is that I think this is so much complexity that it's not likely to happen in nature. Let's not ask whether Alice with her magic wand can create it. I think she can. The question is it something that's likely to happen because the radiation is passing out through a dust cloud? And I think that's extremely unlikely.
Let's thank Lenny again.
Thank you.